Hello and welcome to the third and final video accompanying lecture 25. This is the final video where we're going to be talking about the concepts and background of chapter 28, where we explore an introduction to atomic physics. In this lecture we just have two final topics to discuss. That's characteristic X-rays and lasers. So you've seen this figure before. You saw this figure in lecture 27 where we talked about quantum mechanics, because we introduced the idea of the X-ray and talked about how there's these quantized vibrations, but there's a continuous spectrum that's created, the Bremsstrahlung. All right? So this continuous curve represents Bremsstrahlung, the shortest wavelength depending on the acceleration voltage. All right? So this has to do with the X-rays reflecting off of the atoms in a material, because this entire graph here is produced by bombarding, like some sort of metal sample, with high energy photons called X-rays. These are very short wavelength, high energy photons. But we mentioned the spikes before, but here we're going to talk exactly about where the spikes are coming from. So when a metal target is bombarded with high energy electrons, the metal emits X-rays. So I'm sorry, we're not bombarding it with photons, we're bombarding it with electrons. The X-ray spectrum typically consists of a broad continuous band and a series of intense sharp lines. Right? So the broad band has to do with the idea of electrons, producing high energy light. But why the two big spikes? What are causing these? So these discrete lines, that's the spikes, are called the characteristic X-rays, and they're characteristic for that particular metal, for the atoms that make up the metal. And they were discovered in 1908, but their origins remained unexplained until the details of atomic structure were developed. Okay, as we know, turning points in 1913 with the Bohr model, and further corrections with solutions with the Schrödinger equation and the Dirac equation in the 1920s. Okay, so when a high energy electron collides with an electron in an inner shell of the target atom, it can sometimes impart enough energy to remove the electron from the atom. The vacancy created in the shell, this would be like the S shell, for example, of n equals 1, is then filled with an electron in a higher level when a higher level drops down. All right? And which takes about 10 to the negative 9 seconds, so about 1 nanosecond. All right? During this transition, a photon is emitted with the energy equaling the difference in the energy between the two levels, right? Because there was some higher energy electron, and now there's a gap, right? It's empty, so that electron's going to move down. But this energy gap here is quite large, and so it's going to produce a very high energy photon, which would have a very short wavelength, X-ray short, right? Much shorter than visible light, shorter than ultraviolet. Okay. All right. So typically the energy of such transitions is greater than 1,000 electron volts. All right. So this energy gap is greater than 1,000 electron volts. Compare that to the ground state energy of a hydrogen atom, which is only 13.6, right? You could ionize that single electron in the hydrogen atom almost 100 times over before you could get enough energy to knock out one of these inner electrons of a heavy atom, an atom that makes up a metal. All right? So there's a lot more energy of these bound electrons. I'll kind of speak to that in just a second, but first of all, take note of the numbers. So let's assume that the incoming electron has dislodged an atomic electron from the innermost shell, the K shell. If the vacancy is filled by an electron dropping from the next higher shell, the L shell, the photon emitted in the process is referred to the K alpha line. Okay, that's the K alpha line. That's actually the most probable one. That will always, for these most common metals, that's going to be your higher line, because that's happening more frequently. That's greater intensity. Okay, the probability speaking, it's more likely to occur, probabilistically speaking. Okay, so that's our K alpha line. If, however, the vacancy is filled by an electron dropping down from the M shell, which is also possible, I mean, some electrons going to fill that gap, it doesn't have to be one from the closest shell, then that is called the K beta line. Okay? Other character X-ray lines are formed when electrons drop from upper levels to vacancies other than those in the K shell. For example, L lines are produced when vacancies in the L shell are filled by electrons dropping down from other shells, any shell higher than L, all right, such as M. Those are called the L alpha lines when an electron drops from the M shell to the L shell, and the L beta line when an electron drops from the N shell to the L shell. Okay, but the ones we primarily talk about are the K lines. Okay, and they're K because that's the shell that's getting vacated. that had a vacancy in it. Okay, so why are the energy levels so much bigger? Let's take a look at the equations. Okay, so first of all, there's something called the effective Z number. Because remember, Z was a variable that we introduced in one single slide. I'll reiterate it in examples next week. That corresponded to the number of protons in the atomic nucleus of hydrogen-like atoms. That's atoms that have a single electron. Okay, but here we're talking about Z effective for non-hydrogen-like atoms. So these are atoms that have lots of electrons. They're not mostly ionized. And so we have a new thing. We're minusing 1. The reason we do that, the reason we subtract 1, is because since this is not a hydrogen-like atom, that innermost shell, the K shell, is more like helium-like because it's got 2 electrons in it, and that other electron does some shielding, thus making it so that the electron that's being held onto is slightly less bound than it would be otherwise. Okay? But why are the binding energies still so high? All right? Well, here we have the value of what's going on, right? So we got the mass of the electron, the charge to the 4th, Planck's constant divided by 2 pi, which is h bar squared, everything the same, right? But here's the thing, Z, right? What elements are we talking about here? Well, we might be talking about, say, gold. Well, let's go back to the periodic table, right? Well, Z is a number that refers to the number of protons, okay, unequivocally. So then it turns out that the number of protons is also known as the atomic number. So Z is none other than the atomic number. So if I was bombarding gold, trying to produce X-ray emission from gold by bombarding of high energy electrons, well then I'd have 79 for my Z. So sure, I subtract 1 from it because of that partial shielding of the other electron in the K shell, but that still gives me 78. So then when I go to the formula, I have 78 squared. Well, 78 squared is a huge number. No wonder it's so much bigger than 13.6. Okay, so mathematically that makes sense of why we're producing such higher energy gaps. But why are they such high energy gaps? Well, because you can think about it as those inner shells in a very large atom as being very squeezed in. They're deep, deep down in the well. Because that well has effectively got much deeper because of all the electrons that are stacked on top of the K shell. All right? It's like if you dug a well and then filled it with a very, very dense liquid, thus crushing the ground underneath it, making the well deeper as you filled it. Okay? All right. So there we have the idea of characteristic X-rays. Numerically, you can see, as you would actually solve the problem, it's kind of similar to doing hydrogen-like atoms. You just got to pay attention to kind of what type of problem it is, whether it's a character X-ray problem or it's, say, the energy levels of, triply ionized beryllium. Because slightly different questions would be asked. In this case, you're finding, really probably the energy level of the incident electron or something instead of the energy gap between particular shells. Because here, there's no going between shells so much as just a vacancy getting filled. Okay? So, but again, hopefully, seeing examples of that will make sense. All right. And this is experimental confirmation. So in 1914, so I guess 1 year after the publication of the Bohr model, Moseley plotted the Z values for the number of elements against the square root of 1 over the lambda, where lambda is the wavelength of the K alpha line. So that's electrons getting vacated from the K shell and then getting filled from the L shell. So he did it for each element, and he found that such a plot produced a straight line as shown in the figure, which is consistent with the rough calculations of the energy levels. Right, because we should expect a linear line once we take a square root relationship between lambda and Z. Okay? And so it's experimental confirmation that this idea of kind of thinking about the inner shells as being sort of shielded hydrogen-like atoms, then they indeed are. All right? Is it perfect? No, but it's a pretty darn good approximation. All right? Okay, so last topic. This is understanding a little bit about atomic transitions in the context of lasers, or maybe it's more understanding lasers in the context of atomic transitions. But it's a nice little application. It's a good story. So here's the idea. So we know that an atom will emit radiation only at certain frequencies that correspond to the energy separation between the allowed energy states. All right? So the energy of the photon has to equal delta E, right? So delta E equals the energy of the photon. Okay? And the energy of the photon is going to equal, HF. Okay? That's energy of a photon. We've seen it a few times. Good thing to make sure you have that readily available. That's energy of a photon is always Planck's constant times the frequency of the photon, or h times c over lambda. Okay? Okay. So let's consider an atom with many allowed energy states, as shown in the figure. All right, on the left. When light is incident on such an atom, only those photons with energies of HF matching the energy separation delta E between two energy levels can be absorbed. Right? That's the idea of absorption lines. That's why there's only particular absorption lines. A schematic diagram represents the stimulated absorption. Okay, that's what this is. All right, this is the idea of stimulated absorption, before and after. Before and after. Stimulated absorption. It's stimulated because you're putting energy in the form of sending light into the atom, and in doing so, you're stimulating absorption. You're causing that electron to be more at a higher energy state, thus giving the total atom more energy. Less bound energy, right? It's approaching zero, but it's got more energy than it had before, because before it was in a deep, deep well. Now it's in a slightly less deep well. Okay. All right, so if a vessel containing many atoms of a gas is illuminated with a light beam containing all possible photon frequencies, a continuous spectrum, only those photon energies, E2 minus E1, or E3 minus E1, or E4 minus E2, and so on, can be absorbed. So some atoms are raised to various allowed higher energy levels called excited states, right? So there's only particular colors within that broad band of the white light that you're shining in that are going to work to stimulate electrons, but they will work if they crash into an atom, and they will stimulate the electron, and then that electron is now in an excited state, and so the whole atom is in an excited state. Okay, terminology-wise. Stimulated absorption. Again, this is really restating what we saw before when we looked at that absorption diagram, right? When we looked at, here, this one up here, where we saw the rainbow with the black bands, right? That was precisely the idea that we're discussing right now. Okay, but now we're going to continue that idea a little bit more. So let's get back to that. Okay. So once an atom is in an excited state, there is a constant probability that it will jump back down to a lower level by emitting a photon, as shown in the figure. This process is called spontaneous emission. All right, and it usually doesn't take very long. You know how we talked about how there was like that 1 nanosecond before the electron is relaxed? Same idea here, about 1 to 10 nanoseconds. Okay, it's going to drop back down to that lower state. But here's the thing. We can actually encourage it to drop down more reliably, even faster. Okay, so a third process, this is the important one for lasers, called stimulated emission was predicted by Einstein in 1917. Suppose an atom is in that excited state. So we happen to capture it during that 1 nanosecond of window of time, while it's still in an excited state. And then another photon with that exact amount of energy passes by, right? So this is an energy with the exact matching energy. So it's a identical twin photon is the one that allowed for the excited state in the first case. So if that identical photon passes by, it'll actually encourage the electron to be relaxed, all right? And so the incoming photon increases the probability that the excited atom will return to the ground state, so emit a second photon. Note that the two identical photons resulting from stimulated emission, all right? The emitted photon is exactly in phase with the incident photon. Check that out. So stimulated emission, and we're not explaining all the physics of why it should encourage it to happen, other than to think about the fact that the waves are kind of in phase, so there's kind of this resonance that's occurring. Well, but the important thing is that once the two waves are produced, in this case the two photon waves, now our matter wave has changed back to another state, but this, because they're all waves after all, but these two photon waves are exactly in phase. Okay, and that should kind of make you start thinking about lasers, because lasers are in phase light. That's one of their characteristics. They're monochromatic and it's all in phase. Okay, it's completely there's no randomization in terms of the phase, which is why it can be so bright. Okay, so the intense coherent meaning in phase light in a laser is a result of the stimulated emission. In a laser, voltage can be used to put more electrons in excited states than in the ground state. This process is called population inversion. All right, so you have a population of atoms where most of them are in an excited state. Population inversion. Okay, and then this is stimulated emission. Okay, so the voltage is kind of a new idea, right? So you're charging up that gas, you're kind of getting it all excited. Now it's going to want to start just emitting light, but then it turns out that there's already incident light, right? This first photon here, incident light. And so then instead of it just kind of randomly emitting light, it's emitting a bunch of in-phase light. There's one other thing, is you want that inverted population to be in metastable states, which is why certain gases work better than others for lasers, because you want that time to be in the excited state to be as long as possible. You want it to be on the higher end of 10 nanoseconds rather than the shorter end of 1 nanoseconds, because there's natural variations between elements. Okay? Thus, you've got a laser. In fact, laser is an acronym. The word laser is an acronym that stands for light amplification by stimulated emission of radiation. So that stimulated emission idea is a real kind of crux about what makes lasers work. Okay, so kind of good illustration of it. All right, so here we have a figure. So the figure is the energy level diagram for a neon atom and a helium-neon gas laser. The mixture of helium and neon is confined to a glass tube sealed at the ends by mirrors. A high voltage applied to the tube causes electrons to sweep through it, colliding with the atoms of the gas and raising them into an excited state. Neon atoms are in their excited state of E3 through this process results in collisions with excited helium atoms. When a neon atom makes a transition to the state E2, it stimulates emission by neighboring excited atoms, which produces coherent light at a wavelength of 632.8 nanometers. Right? So we see that there's this process of creating a metastable state due to the different energy processes of colliding gas molecules, the two different particular gases that are chosen. And also that mention of mirrors is important, because actually I had intended a second ago to point out that in order to cause a greater probability of stimulated emission, you need those incident light photons to be interacting with a lot of atoms. The best way to do that, rather than just having a single wash of photons pass through your gas once, is to have your light bounce back and forth through your gas. So lasers then would have mirrors and just small apertures that then will emit the eventual effect of all these atomic processes. All right. So we got one other schematic to look at. So this figure summarizes the steps in the production of a laser beam, kind of showing it in a more kind of full way with the mirror included, kind of a full kind of engineering schematic, but of course a very cartoonish one of what's going on. All right, so lasers that cover wavelengths of the infrared, visible, and ultraviolet regions of the spectrum are now available. Applications include the surgical welding of detached retinas, LASIK, known as LASIK surgery, precision surveying, and light measurements. All right. So we can think of the many applications of lasers and just their general kind of over-the-shelf accessibility and fun as laser pointers or playing with cats. Okay? All right, so I hope this was a good kind of final summary to bring these ideas together. I would highly recommend taking a look at the slides that I've posted. I've posted the slides including all of the lecture notes that or discussion notes that I am referring to in these videos. Also, another added bonus of looking at the slides that I post is you can check out the summary, which gives a nice summary of all the equations. Good thing to refer to make sure you understand all the steps and maybe jump back and listen to a particular part of the video. Furthermore, please look out for lecture 26 on Tuesday, where I'm going to actually show some simple numerical problems involving energy levels of Bohr atoms, counting number of states, characteristic X-rays, and the like. All right, so thanks for watching.